So far, we've looked at the parent functions for sine and cosine. And hopefully it won't come as a shock to you to hear that what we're going to do next is transform those parent functions. We're going to look at those functions, but moved around, just like all our other families of functions. We did the same thing with absolute values and square roots and cube roots and quadratics and cubics and rationals, a little bit different. Logs and exponentials. We've done the same thing every unit of the year. We have taken the parent function and then moved it around. And what we're going to see with sine and cosine is they get moved around exactly the same way with the a, b, h, and k. We're not going to talk about h today. We'll save that for another class. And the slight catch is that there's a specific vocabulary for the a, b, h, and k when we're talking about sine and cosine that we don't use for other types of functions. But once you get over that vocabulary, it's the same movement. So let's kind of dive into that vocabulary. First off, every sine function has something called a midline. It is the horizontal line through the middle of a function. Very important to realize that it's horizontal. So it's a horizontal line through the middle of a sine curve. And every time I say sine curve, that applies to cosine also. You'll see later today that they're really the same thing. Now, normally, when we graph just the parent function, which would be right here, that midline is right on the x-axis. The midline for the parent function is y equals 0. But we can move the midline up or down the same way we move any other function up or down, simply by adding a k. That's it. So whatever the k is, moves the curve up or down. So this curve that's graphed here, it must have had a k that was positive, plus k. So what we've been calling the vertical shift all year, the k, in the context of sine and cosine, we're going to call it the midline. Very important to realize that the midline is a line, it's a horizontal line. So when we write what the midline is, we always write it as an equation, y equals k. And then the other piece that we've seen all year long is what we've called the vertical stretch, taking a function and stretching it, making it steeper. Well, in the world of periodic functions, sine and cosine, there's a name for that too. It's called the amplitude. A slightly more technical definition is that it's specifically the vertical distance from the midline to the maximum value. So going back to our parent function again, I'm going to drag this down here just for a moment. The amplitude here would be the distance from there to there. And we know in the parent function that we get as high up as 1. If it gets higher than 1, that means the amplitude must be bigger. So the amplitude is that distance. And just like we know that the way you do a vertical stretch in any other function is by putting a coefficient in front of it, same thing here. That coefficient in front, which is what we'll call our a, just like in every other function of the year, is the amplitude. So if we take a look at a generic function, y equals a times the sine of b theta plus k, whatever that k is the midline. And so what I want you to be thinking is that there's actually a there's an invisible horizontal line, and I make it really as light as I can. Make it light gray. You can barely see it. But however high up that is k. And that's the middle of our graph. And then the a is the amplitude, which means it's the distance between our midline and our max, which means the maximum is going to be up here. Of course, the sine goes just as far down as it does up. And so the minimum value will be exactly as far below the midline as the maximum is above. So here's our max, here's our min, which means our sine curve is going to go up and down from that high to that low to that high to that low, and it'll keep going just like that. Which means the range, the lowest y value to the highest y value, is everything from k minus a to k plus a. Because that's the highest that we get here is k plus a. A technical note, if we want to be specific or be like really correct here, the a in front of the sine curve can be negative, and we'll see examples of this later. Amplitude is always a positive value, so technically speaking, the amplitude is really the absolute value of the a. So what we're going to see here in these two examples is how we use this amplitude and midline to graph a sine curve. Your first step, and I always want you to think in this order, we did midline first and then amplitude. We're going to do that every time. Every time you see a sine or cosine graph, you're going to think first, okay, what is the midline? What is the amplitude? So in this case, the midline is k equals -1. So that's your midline. Y equals -1. And so what you're going to do is, as soon as you identify that, actually, I'm sorry, not quite yet, and then the amplitude is 2. So we can use that to identify the range. I want you to do those three things in that order every time you see a sine or cosine function. Midline, amplitude, put them together to make the range. So the range is going to go from as low as -1 minus 2. It's going to go as low as -3. And as high as -1 plus 2, as high as 1. In other words, the middle of our curve, and the reason I did that before drawing on the curve is because I wanted to make sure that we make a scale that makes sense. So if I'm going from -3 to 1, it makes sense to say, all right, I can count by ones here, and I'll be able to fit everything nicely. Had the range been like -30 to 10, well, then I wouldn't be able to count by ones on this graph. So now that I have my y-axis marked from -3 to 1, I can say, all right, the midline is at -1. And so what I'm going to do is draw a very light little line there. And I'm going to draw another very light little line at the max, and another very light line on the minimum. And my sine curve will go from the midline up to the maximum, and then back to the midline, then down to the minimum, and then up to the maximum again. We'll talk about the x-axis in just a minute, but for now, it's understanding the y values here, how you know what the lowest and highest points to put on your y-axis are. So we'll go through this process one more time with the second example. Y equals 1/2 cosine of x plus 1. Again, the order is midline, amplitude, range. Think those three things in order. The midline is y equals 1. The amplitude is 1/2, which means my range, my values are going to go from as low as 1 minus 1/2 and as high as 1 plus 1/2. You can write these as decimals or fractions, whichever you prefer. I like fractions, so I'm going to stick with 3/2. And because I only need to go as high as 3/2, what I'm going to do here, what I really should have done is not graphed my x-axis at all, because I don't need this negative space down there. It's just wasted, but oh well, what's done is done. So what I'm going to do is count by halves. So I'm going to label my y-axis by halves, so that way I can fit everything on here nicely. My maximum is 3/2. My midline is 1. And my minimum is 1/2. Draw those little lines there, and then I can connect my dots. Notice, however, this one is a cosine, which means it doesn't start at the midline like my sine did. It starts up at the max, and then goes neatly through all 4 of those next points. One thing I want you to notice about the way I drew the cosine in particular, I do want to draw arrows on the edges of those graphs. When you get to your intensified pre-calculus class next year with Mr. Lenowitz, he will tell you not to. You can't fault the man for being wrong about one thing every once in a while. But if you're going to draw those arrows, just make sure that you don't draw the arrows pointing up, because the cosine curve, it doesn't go up. It turns around before it continues on with its cycle. So make sure you kind of draw, like show the cosine curve coming back down before you draw the arrow. The next thing we're going to talk about is the period. The period is just like the horizontal compression of a regular function that we've been dealing with all year. Sort of. It's based on the horizontal compression. Technically, the best definition for the period is the horizontal distance between the start and end of each period. We can say between the start and end of each cycle. So if I were to just quickly draw a sine curve here, I'm not going to label it with numbers or anything, just draw the curve. The period is the distance from here to here. This distance is the period. Now, the period of our parent function, we know it ends here at 2 pi. So the parent function has a period of 2 pi. But just like any other function, we can compress it or stretch it horizontally by putting a coefficient in with the x, or in this case, in with the theta. So just like any other function all year, we're going to see some that are all squished together. Or we're going to see some that are stretched out. So I'm not even going to have room to finish. And the way it works is a pretty simple formula for calculating the period. And remember that we're basing this on the equation for any sine curve is a, which we already talked about, times the sine of b theta plus k. We already talked about the k, we talked about the a. It's the b that has to do with the period. But be careful. The b is not the period. It's really, really important that you kind of remember that from the beginning. The b is not the period. The period is there's a formula for calculating the period. The period is equal to 2 pi over b. Remember when we've been doing our transformations all year long, when there's a b, we know to divide the x values by b? It's the same idea here. We're dividing by that b. By the way, or if we happen to be working in degrees, we would just replace that 2 pi with 360 degrees. Just so you know, if you ever need to find the b based on the period, which we have to do when we see the graph but don't know the equation, the conversion works exactly the other way around. B would be equal to 2 pi over the period, or 360 degrees over the period. That would be how we would find B if we already know the period. Like in this example right here. Find the amplitude and period of the function graph below. Well, let's start with the period. We can see that the amount of time it takes for this graph to be finished, it's a sine curve. It goes from the midline, it goes all the way up, it's the middle. That's not done with the period yet. It hasn't gone down yet. It goes all the way down and back, and it is finished by the time we get to pi. So the period is equal to pi, which means if we are going to figure out what that b is in the equation, because the directions tell us to write the equation of the graph, we can say that the b is equal to 2 pi over the period, which we can simplify to 2. So our b is equal to 2. Our a, right, because we look at the sine curve and we see the amplitude is not 1, doesn't get nearly as high as 1. This amplitude right here, we can see that distance is about 1/4. Looks like it's supposed to be exactly 1/4, or you can write 0.25. So our a is 0.25, or 1/4. And notice that there is no vertical shift. The midline is right on the x-axis at y equals 0, which means that the k is equal to 0. So we have just figured out the b, the a, and the k, and we can put that into our equation. Y equals a times the sine of b theta plus k. And so in the next videos, we're going to start from scratch and graph some of these equations that have a's, b's, and or k's, and see how it all works together.